This lesson deals with voltage and Kirchhoff's voltage law. You can find these notes in the course ebook in Chapter 2 starting on page 5. The next term we're going to find is voltage. Voltage, or potential difference between 2 points, indicates the energy required to move charge from one point to another. In other words, voltage is the change in energy per change in charge. If you make that change small enough, it becomes a derivative, where V is voltage in volts, W is energy in joules, and Q is charge in coulombs. A plus and minus sign, or a polarity, is used to indicate the voltage across an element. Voltages, like currents, can be positive or negative. Some terminology. If I have a two-terminal element between A and B, and A is the plus sign and B is the minus sign, then we say you go through a drop in voltage in going from A to B. Also, if you go from B to A, we call that a rise in voltage. Energy is lost in going through a drop in voltage, and energy is gained in going through a rise in voltage. Before we talk about Kirchhoff's voltage law, we need to have a few more definitions. The interconnection of two or more circuit elements is called an electrical network. If an electrical network contains at least one closed path or loop, we then call it a circuit. Now, a closed path or loop exists if you start at one node and you can return to that same node without traversing a circuit element more than once. And that's a mouthful of words. Let me take an example here and show you what I mean. If I start at a point and I go around a loop and I don't go through the same element more than once, then that's a circuit. Here, if I start at this point, go around this path, it's not a closed loop. I have to come back to get back to that same start point. And this is not a circuit. Now, energy is lost in moving a group of charge from point A to point B. Now, since voltage is the change in energy per change in charge, then the energy that we lost in going through a drop in voltage would just be cross-multiplying here as the change in charge times the voltage drop. Likewise, you could say that energy is gained in moving that same amount of charge from B to A through a rise in voltage. And the same equation, the energy that we would gain would be the change in charge times the rise in voltage. In doing Kirchhoff's current law, we talked about the postulate of the conservation of charge. There's also a second postulate that's used in electric circuits and electronics, and it's called the conservation of energy. Again, postulates are things that we assume to be true for a class of anything, and then there's properties that follow from it. A good example would be geometry. Let me state the conservation of energy postulate. Energy can neither be created nor destroyed, although it can be changed from one form to another. So whatever energy we absorb would have to equal whatever was generated. Now we can use that to prove Kirchhoff's voltage law. So let me state that first. Kirchhoff's voltage law is the following. The algebraic sum of the voltage rises equals the algebraic sum of the voltage drops around any closed path or loop. Now, why is this true? Let's consider a simple example where I've got 5 elements, and I'm going to assign voltages V1, V2, and V3, and V4 and V5. And suppose I take a clump of charge and I move it along this path, or closed loop. So I'm going to have a drop in voltage, or a loss of energy, of the change in charge times V4 times the change in charge times V5. Now, taking that same charge to a rise in voltage, we would then gain energy of the change in charge times V3, the change in charge times V2, and the change in charge times V1. By the conservation of energy, the energy that was lost must equal the energy that's gained. So if we take the energy that was gained and set it equal to the energy that was lost, what we have is a common delta Q. So you can divide through by that. What you're left with is that V1 plus V2 plus V3 is equal to V4 plus V5. So the rise in voltages, and we went around in a clockwise fashion, would equal the drops in voltages. Let me do an example to show you how to use Kirchhoff's voltage law. Here I have 5 elements. I'll assign voltages V1, V2, V3, V4, and V5, and I'll later show you how to pick these. How many paths or closed loops do we have? Well, there's one here. There's one here. And there's one around the outside. So if we perform Kirchhoff's voltage law around loop 1, I'm going to go around clockwise. I have a rise in voltage of V1, a drop of V2, and a drop of V3. So V1 is equal to V2 plus V3. If we were to go around loop 2, just starting here and coming back to the same start point, I have a rise in voltage of V3, a drop of V4, and a drop of V5. So V3 equals V4 plus V5. Lastly, there's an outer loop. Again, I'll start over here and I'll work my way back around. So the rise in voltage is V1, the drop is V2, the drop is V4, the drop is V5, and we're back to our start point. So V1 is equal to V2 plus V4 plus V5. There's also an interpretation of signs for voltages. So if I were to have an element connected to a circuit, and I had a drop in voltage and it had a value. Suppose I wanted to change the sign that's here. So if I were to make this a drop in this direction, then what I need to do is to change the sign of the quantity in the parentheses. Just like current, changing the direction means you change the sign of the value. So now I've got a drop in voltage of -3. Here I've got a rise in voltage of +3. It means the same thing. Let's take a look at an alternative form of Kirchhoff's voltage law. If around a closed path or loop, voltage drops are added and voltage rises are subtracted, then the algebraic sum of these voltages is now 0. Now why is this true? Let's go back to our example. Let me change these drops in voltages to rises in voltages by changing their sign. So -V1, -V2, and -V3. Now if I go around this path, everything is now a drop in voltage. So no rises in voltage. If you're to put these last three terms on the other side of the equation, you have the same equation we had on page 8 in the proof of the first form of Kirchhoff's voltage law. Again, sometimes this is very convenient to have a 0 when you're doing a proof. I find this a little more complicated than doing the first form of Kirchhoff's voltage law, but both are equally valid, and I'll tend to use the first one. Let's revisit that example and use the alternative form of Kirchhoff's voltage law. So if I'm going to go around loop number 1, so I have a rise in voltage, so I'm going to subtract that. So minus the quantity V1, a drop of V2, and a drop of V3, and that equals 0. Go around this loop, I have a rise in voltage, so a minus V3, a drop of V4, and a drop of V5. Go around the outer loop. Rise in voltage, so I'll subtract it. Add V2, add V4, add V5. Again, equal to 0. I find this very confusing, and there's a little bit easier way to do this, and that is as you go around the loop, is just to write down the first sign that you see. So here I go around the loop this way, I see a minus the quantity V1. I then see a plus V2, and I see a plus V3, and set that equal to 0. So that's another way you could look at the alternative form. Again, these are all the same in terms of the results. I find the first one easier than the second form. And this is the definition of voltage and Kirchhoff's voltage laws.